I'll be largely focusing on Decile.org and its applications. Um, yes, well, a lot of it has some modularity. Okay, yeah. So a lot of it will be, of course, leveraging some modular functions, but not necessarily completely. So recap that illustrated somewhat there with some tutorials. In fact, I had kind of run through some of the tutorial notebooks and also kind of as a homework um, asked you to run through these. If there are any questions, let me know. For general submodular functions, submodular mutual information, conditional gains, and conditional gain mutual information. Then there was also an image summarization demo we ran through. So this is the use case of trust I talked about, which packages some of those to do targeted subset selection. For example, you can have this one, active learning. The use case of active learning. Actually, yeah, active learning is one use case, but for rare class enhancement. So you have some nighttime images, you try and find a subset of the unlabeled data set that's aligned. Right? So aligned subset of the unlabeled data with the target images, which you then label. The argmax of I of x comma t, argmax over x. This will give you the target subset, which you label. You could also do this for performance-based data selection, or you could use this for personalizing, say, handwriting recognition. So there are multiple algorithms implemented within Trust. But I will now move on to the next one, which is Peer. Okay, so I'll be doing a little bit more details on this. It's data programming and subset selection. So how does subset selection even come into play here? Let's understand the big picture here. This is a setting again called the cold start setting, where you don't have too much of labeled data. So recap, I talked about this picture. I don't even I talked about this picture, right? So you have cold start using Trust. You could also have cold start using Sphere, semi-supervised data programming, where you have very less labeled data, no labeled. Okay, so reduce labeling efforts using data programming. What is data programming? You begin with, say, some labeling functions or rules. For example, if text contains how, the question is of type description. If the text contains how long, it's of type numeral. Simple, right? But these rules conflict. Therefore, there's a need for what is called label aggregation, where you're sorting out or creating consensus between conflicting labeling function. Okay, so this is the idea here. It's not just one. Each of these, all of these create consensus. And this is very important, especially when you are considering resource constrained machine learning settings where you can't afford the luxury of having all data instances labeled. It also is very aligned with the fact that even when you ask humans to label, you give them some annotator guidelines, right? Now, all you're saying is if there is a scope for converting your annotator guidelines into labeling functions, then why not? Okay, so here's an example, another example. Barak and Michelle visited Stanford University with their daughter for a college visit. Write a simple program that labels +1. The people in the example above are married, -1 if they are not married, and 0 if the program is unsure. Right? So often you provide annotator guidelines to the annotators. These could be converted into labeling functions. Okay, so we are saying and these are basically programs. LF example between example.person and example.person2 and after example.person2 and their daughter, that word their daughter is there, right? If that their daughter is there after example.person2, then return a 1. Of course, no, Vinith, who's here, could explain a lot more. Please help code up the entire Sphere platform. Now, you could apply these to unlabeled data and create consensus-based annotated examples. But optionally, what you could also have is some labeled data. And this is where we'll talk about use of subset selection. You could have or see labeled data which potentially complements the LFs on unlabeled data. Okay, so that's a use case. So labeled data is therefore, we'll come to this little later. It's there in dotted lines. It's optional. So we'll first begin with the rest. I'll give you examples for all this. We'll begin with this rest, and here also we will talk about some of these specific cage, for example. So we'll begin with this. And then we'll bring in label set subsequently. And we'll also talk about how to intelligently subset the label set. What is that label set? Why such a label set is required? Why a labeling function is not sufficient? Okay, so I mean, this is a big problem definition. I'm also hoping that some of you get inspired to tackle this big real issue, right? The reality is we have some data instances and some maybe label set well, we hope to have. But often what you have is a large unlabeled data set. You may have labeled set, but it may be partially labeled or you may have none of them. But you have labelers, both human and machines, possibly noisy and untrained. And you can think of them as having some parameters lambda. So the idea is you want to even learn those parameters lambda. And so tau ij is like the response of labeler lambda j when triggered. Tau ij is 0 otherwise. Think of these as outputs of those labeling functions or programs. And I would say the realistic goal is expand the labeled data set, minimize labeling cost, and train any lambda j's that are trainable, right? So this is, you may have none, in fact, as I said. You might have no label set to even begin with. Okay, so Okay, let's look at image labeling. Right? So you could have human labelers, you could also have machine labelers, or you could have non-ML based labelers. Right? You could probably just do template matching. I can have exemplars. I can have an example of a god right here, or example of bananas. So could be rules, LFs, or exemplars. Right? Um, could be object databases that you're looking up. That's how things use face recognition is to function before deep learning setting. And you can see that these labelers could give different weightages. Indoor 68%, whatever, right? Claw. In fact, these are very weakly trained models, and you can see they're all over the place. In fact, some labelers or some labeling functions, they are pretty precise. Some of them are not, right? Some of them give scores, some of them don't give scores. So this is give. So some of these might give scores. Some labeling functions might emit scores as well. Whether the percentage or whether they are fractions is not a big deal. Some are just discrete. These are discrete labeling functions. Okay, so we want to make sense of all of these across multiple images, multiple instances. Okay, and so the first objective would be labeler reliability. I mean, you can see that these labelers have some complementary expertise. Some labeling functions seem to be doing well right here. This labeler seems to be doing well here. Whereas we are quite concerned about labeler C altogether. It seems to be too spreading itself too thin, right? Labeler B seems to be okay on this, but not very good here for the first set of objects. So you want to kind of make overall sense. As I said, these could be human, but we'll talk about programs. For us, these are like these are going to be largely programs. Who wrote the program? Whether the program itself is an ML model, we'll concern less about it. For us, these are black box programs. Black box, but consistent programs, right? So they don't have a random element to it. Therefore, we can profile them. Whose performance can profile. Okay, so the second is now our first objective is profiling the labels, right? Second is after profiling, what you want to do? You want to do collective prediction. You want to aggregate the label predictions from individual labels to generate consolidated high confidence label predictions for each instance. So here we have kind of shown where you would like to be. You would like to say, okay, it's a clock, not a dog, right? Like to say it's a second one, it's a banana, it's a fruit, it's not a vegetable. Right? So maybe there are other labels from other labelers as well. So and now going back to text, we'll take more text and then come back to images later on. Right? So these are examples of labeling functions. If some word in spouse dict is present between E1 and E2 or within two words of each other, return else, one else, return 0. You can actually design these, not very difficult at all. And yeah, Sphere lets you design all of these. Now, let's say that the labelers are the labeling functions, okay? So let's say you have lack of human label data, human design labeling functions assigning noisy labels or instances. Use these labels to generate label data. This is exactly the goal of data programming. So there's some existing platform at Stanford called Snorkel. and like, I mean, for example, it has one discrete probabilistic graphical model where you look at the lambda parameters associated with the labeling functions and labeling functions. For a particular instance I, look at the output rather, sorry. Look at the output of the labeling functions for instance I and try and consolidate its labels into this yi. That's what it tries to do. So I mean, direction is not important, but the idea is you go from the labeling function outputs to the desired label. And what it does is it has shared parameters for agreement and disagreement of labeling functions. Okay, I'll talk about that. So as I said, we begin with the labels assigned by the labeling functions. Let's say there are n labeling functions. Okay. So you had this lambda 1, I1 to lambda in are the labels assigned by the n labeling functions to instance I. Some instance I. So what it lets you do is says, okay, I am going to have these p theta parameters. Theta is a parameter and associated probability distribution p theta, where it's trying to maximize some joint probability distribution through these potential functions exp phi j. Right? Phi j is basically looking at the signal associated, the strength of the signal associated, or the value to be given. That's the value to be given to a signal associated with the ith example for the jth labeling. So if lambda ij equals kj, that's how it says. Kj is the kth label, jth label. So if indeed lambda ij says kj, then associate parameter theta jy. Otherwise, make it parameter minus. If it doesn't agree, then the phi j should be minus theta jy. So think of this as the potential. Okay, so this is what Snorkel did, and that's like a base model. Now it's unsupervised. That's an issue. But the bigger issue, which we delve into our 2020 paper, is that it's very highly sensitive to initialization, number of epochs, learning rate, etc. Okay, so when you do some gradient descent, right, on this. So what you're trying to say is these are the issues of solving. You can solve it using an iterative scheme. But even without iterative algorithm, these are issues. Why? Also because I won't get into the details here. You can look at our paper, but it turns out that you can just flip the association of the labeling functions, the theta parameters, for example, just flip them. Okay, so this instead of theta, you make it minus theta, this make it plus theta. And it turns out that the likelihoods can be maximized with something silly like this. Because it's unlabeled. You don't know what are the YJs, right? Okay, so that's one. And the second is that it does not support continuous labeling functions. This basically requires lambda ij equals kg, right? So this is just discrete matching. Sorry? So it can, so the point is a labeling function can also abstain from labeling. So this is zero otherwise. Let me just highlight it. So this basically says if j labeling function abstains, or just if labeling function abstains from labeling. Okay, so you can also abstain. Like human labelers will say, I don't know the name. I won't do it. Yeah, but ultimately the match is discrete, so it does not support continuous labeling functions. Okay. So then we brought out one solution to the snorkel issue. He says continuous and quality guided labeling functions. So quality guiding is the issue I brought up at the top, right? The high sensitivity. So we say, well, we can do quality guiding. And we also brought in continuous so that can deal with deep learning, embeddings, and so on. So given n labeling functions, which can be continuous or discrete, now we have a slightly different model. That each labeling function lambda j for a given instance xi outputs a label lambda ij equals kj if triggered, else outputs 0. So in some sense, it looks like the previous one, but it can also have lambda j as a continuous value output. So it can also output a score, which is what we wanted through continuity aspect, right? Sij could be between 0 and 1. Okay, so therefore now you see there's a tau I1. So it's basically saying if whether it's triggered or not, right? So this first part is saying whether it's triggered or not. And the second part is the score, which is hinting at whether there's a score associated, continuous score associated. Right? So obviously only when it triggers will have a score. Otherwise the score is meaningless. So okay. So let's look at continuous labeling functions. For example, you can say, well, I have a particular dictionary between two words, between E1 and E2, the entities. Look at all the words between E1 and E2. And look at an element of some dictionary called the spouse dictionary. Let's say I was trying to identify whether X is a spouse of Y or not. So I could look at the cosine similarity, max value of the cosine similarity across all U and across all V. So it could be across all U and across all V of elements, U coming from the spouse dictionary and they say V coming from words between the two entities U1. Okay. You could also look at others, and then this is for a particular class. This is for a class plus one spouse relation. There are many others you can design. Like you can look at other dictionaries, changing dictionary, for example, instead of spouse dictionary, family dictionary. Or you could look at the edit distance between U and V. So the seed set. What do you mean by seed set here? Seed set may say Barak and Michelle, right? So you can see Barak Obama. B-R-A-K, right? Spelling is correct. There's a C there. And V is Michelle. Right, so then maybe the text in the text you have something like U is just Bara, right? And V might just be Michelle, not Michelle Obama, right? So you could look at the norm distance of the entities from what U and V are, right? sorry, not Barak and Michelle. I meant E1 and E2. Barak and Michelle. U and B are already specified. Looking at edit distance. So this got continuous functions. And now what we do with these is interesting. So given that we have now continuous course with an indicator continuous lambda j, it's continuous. You can also have discrete only, right? Continuous lambda j is just indicating whether I should consider the score Sij or not. And then tau ij, which is basically, as I said, indicating whether tau ij is 0 means it reframe, or it could trigger exactly for one of the labels. So now we have a slightly modified function, modified potential here. Okay, what is this xi pi? Some explanation is in order here. So here what we do is we kind of associate. The difference I want to point out is we are associating each labeling function with a particular class. So therefore we are saying exp of theta jy. We are not letting it become negative, right? So you see the difference. Xi cannot become negative. Earlier we are allowing it to become negative phi, and that's where the flipping issue was coming up, right? You just flip the thetas and the association class labels, and you will get the maximizing likelihood. But we said we'll change it. So these cannot become negative. Unlike earlier. Unlike the earlier phi. So exp of theta jy, y is a class label, j is a jth labeling function. That is only if the labeling function doesn't fire. Labeling function doesn't reframe. It fires. And it fires me, it must be for that class. That's important difference we made. The second we did was, okay, what if you have, so this is, I made a mistake here. This was for a discrete part. This was a discrete part, okay, not the continuous part. For continuous also we made a change. I'm going to just highlight it here. So this is the continuous part. Highlighted here. So in the continuous part, the difference is that we are using a parameterized beta distribution. So if you're familiar with beta distribution from your basic ML course, it was a prior for what? The Bernoulli, right? So this is like, whether the labeling function fires or not is a kind of Bernoulli distribution. So now beta is like acting as a prior. But even in beta, we have alpha A and beta A, which basically correspond to a prior knowledge of how confident we are that this labeling function will fire. Okay, so you can bring in a prior, though we have found it doesn't make a big difference. So alpha is the prior associated, so to speak, the fact that it will agree. It will basically, it's an agreement of the labeling function with the true label. Alpha t is the kind of prior on the disagreement. So you see this. Let me. So alpha d is this disagreement. Disagreement of what is emitted by the labeling function with what the true label we are trying to estimate. Right? Alpha A, on the other hand, is an agreement prior. and is one otherwise. This, otherwise, again, as before, is when the labeling function refrains. So then the score itself is not useful. Okay, so this is otherwise, and the LF refrains. Continue. Okay, and this gives you overall joint distribution. I mean, the joint distribution. We can also have the Z theta as a normalizer. This is overall picture clear. I mean, the two roles that phi theta and xi theta and xi pi are playing. Okay, so I've given some more details here if you are interested. That alpha A is q, j, c, pi, jy, and beta A are parameters of the agreement distribution. That's exactly what I said above. The parameters, and they are further tied. These parameters themselves are also kind of further subparameterized. So alpha is qj, so qj. It's like it's a quality. It's a quality associated with the labeling function in terms of agreement, quality prior. Okay, and this is a disagreement prior. So I won't go into too much details of these, right? So why this particular choice? But think of these as the mean value associated with the labeling function firing correctly. So that the scores are meaningful based on the prior on that labeling function. Okay, so this is basically the probabilistic model. We'll use this, right? And thereafter, we can just compare the cage model potential. It's always positive. exp theta jy, if it fires, and 1 if it refrains. Whereas the snorkel model potential had this issue, right? So if you said, so basically, if you said k theta j comma plus 1 is minus of theta j minus on the cage model, what would you expect? Theta j plus 1 equals theta j minus 1, minus of theta j minus 1. The cage model, what would happen? Sorry? You'll basically again maximize, right? That's exactly what I was trying to point out. This is the issue. This is redundant parameterization leading to unstable solutions. So basically, you can still simplify cage model to the snorkel model if you couple. So how do you get the snorkel model from the cage model? So you can recover if you want. So first is if you couple the theta jy parameters in phi j. So if you say that the theta jy parameters are coupled, you don't let them so much free. Okay. Not including continuous LFs and the associated potentials. That will again give you the snorkel model potential. So here you see, so the theta jy we kept all of them positive, but for positive and negative, and each labeling function was associated with a particular class. Here you're like leaving it completely free. So here your time. I'm sorry, the other way. What I'm saying is here your time, right? These are being tied. Theta jy if lambda ij is j minus theta jy if lambda ij is not equal to j. So if you couple the theta jy parameters here on the left, you'll end up getting the snorkel model. And not including continuous LFs and the associated potentials will also give you the snorkel model. Next, we'll also show this QJT, which I talked about here. So we'll talk about this QJT. I'll talk about the QJT, which is next. So quality guides. So the QJ C is also kind of quality guide, but it's sitting deep inside the prior. But there's a more explicit prior. There's a more explicit. A more explicit quality guide than QJC. Which we showed in the previous slide. Okay, so I'll just look at that now. Okay, so in addition to this likelihood, we have this very important component, R. This is actually a very important component, which brings stability. One reason I gave you for the instability of the unsupervised learning in cage in snorkel is that the parameterization itself was not really satisfactory. But the other reason or the other way we bring stability is by adding this R. Okay, so likelihood plus R. What is this R saying? Okay, R is basically saying that if I have some intuitive prior about how accurate a labeling function is, say 90%, 80%, or I might be able to say that a particular labeling function LF1 is more accurate than LF2, which is more accurate than LF3. Right? So then I can say that QJ or Q1T is greater than equal to Q2T, which is greater than equal to Q3T. So you can set the Qs to largely honor the ordering constraints. Because if you're giving human rules, you might as well also tell which of them you're confident about. And in practice, we found that the exact numbers don't matter. The range matters. So this is the way of reflecting. So reflecting is ordering. Okay, so match the learned joint distribution of P theta y of phi and tau j with user provided quality guides QJT. This is something user has to provide. And for continuous LFs, parameterize beta distribution to combine quality guides and learning. So there we saw this, we already saw a role that QJC was playing. So that there also there's a role. Yeah, and can empower programs to stabilize training via easy quality guides. We also looked at other options, but I will not get into all of these, right? So sign penalty on raw parameters and all that. We will not discuss this. So this is our view formulation. What is R? All the previous things remain as it is. But now QJT log of P theta y equals Kj given tau j equals Kj. Basically now this is like the KL divergence between the user defined prior and the model prior. Simply that, right? KL divergence between user defined prior and the model distribution. And specifically note this QJ playing a role here. QJ should agree with log of P theta over P theta y equals Kj, and 1 minus QJT should agree with 1 minus P. Okay. Yeah, the rest I will not get into. I mean, how you can write down these expressions is the detail. So now this is your overall formulation. LL theta R on the left hand side, and theta pi on the left hand side, and R on the right hand side. Two together basically give you your loss function. And some of our prior works, we have also looked at other aspects, how interlevel correlation, how you can do active learning sampling. So I'm skipping this, but this is like more on the labeling function characterization. And this becomes useful, especially if you have multiple labels. So not just one label. Let's say you have a label called spam and say nearly spam. Right? So then the two are related, right? Or voice spam versus image spam. Let's say you're looking at YouTube videos. The spam is in the voice. So somebody has created a good frames, but the voice is all messed up. Right? So more on labeling functions and connections with multiple labels. Multiple labels. So you have to look at the connections between labels as well. And in fact, we also look at how you can induce labeling functions, etc. So not just program induction, and I would say ACL. Very recently, we had some paper in can induce. Okay, so this is what I'm talking about. Robust data programming. You have weak supervision and complement the labeling functions with instant features. Additional, very few labeled data instances. So this is where we are going to. Now, instead of only dealing with labeling functions, can we also have some instances, examples which are labeled? I'll talk about that next. And I'll give motivation for that. And we'll try and minimize more equations. We'll not have expressions to deal with. I'm just illustrating the same with image exemplars. Instead of human designed NLP rules, you can also have exemplars, right? So imagine you're trying to organize photos in an album, right? And you can say, well, this is an exemplar. And you must have seen Google Photo Album tries to pick up related images and puts them under that, right? So same, it's my brother. All of these look like my brother. Add photos to an album, and the photo contains person name could be beginning, but then thereafter you could also generalize based on image similarities. Okay, so here you go. These are exemplars, and based on which you found maybe similar people. But you can see that there are some incorrect examples here. It's an incorrect image. Okay, now we see that, well, it's not necessary. It's basically labeling functions, even if you consolidate, sometimes it looks very difficult beyond our perception of beyond the image similarity to be able to determine what this image is, right? Whether it's a brother image or whatever, right? So can label data help? Because it expands the scope, the horizon of what labeling functions do. Okay, so that's what we provide in Sphere. So we provide in Sphere not only the use of cage kind of label aggregation model, but we also let you incorporate labeling for label data. Okay, so this cascaded approach which you see is where I take some labeling functions which give some outputs y1, y2, y3, output a y, and then I take the output and train a discriminative model. So the two are disjoint. The two are completely. There's a Great Wall of China separating the two. So this aggregate or apply aggregation on output of labeling functions. You do that once. Next, train discriminative models on the aggregated labels, right? Whereas what we say is that, well, you don't have to do that. You can use your labeling functions. You can add some label data. plus label data. And that can be, that is what exactly we are having this joint approach. So you don't train a model after labeling the data. You use your labeling functions, guides, you use some label data and learn your model jointly. Okay. So this is a significant departure from Snorkel. Snorkel, which hosts data programming. You just label the data and then use it. Here, the joint approach is a significant departure from Snorkel and previous cascaded approaches. They use label data. Right? The joint uses label data plus labeling functions jointly. Okay, so I'm going to just run you through, I think just to make it more interesting. So let me just go through cage. This is the cage is the previous one, which didn't have any label data. So you can, I'll just go back to cage here. Once stop. These this cascaded approach. I just want to give an idea what these cascaded approaches do. So what they do is you can define a number of hold labels. You can define your preprocessors, continuous scorers, your labeling functions. Some labeling function definitions are here, right? So for the spam, this is the SMS spam. SMS, whether it has is a spam or not, based on a bunch of keywords. And keywords treated as search patterns. You can also look at multiple keywords, their intersection. All these are labeling functions. Some of them, most of them are continuous. Few of them at the top were discrete, right? So you can see continuous ones. They're looking at the amount of similarity, word similarity between words in the text and words in the dictionary. Okay, so then you do so far there's no label data at all, right? So I accumulate all the labeling functions into rules. Now you apply these to data that's loaded. The Y is used not for the labels are used not for any training, right? So I think this should be pointed out very clearly. This is largely to evaluate. Okay, so now what have we done? We have imported the pre-labels class and used to label data. So we have not used any label data. We are creating the label data. Okay, and now this label data, once you create, that's the left part, right? That was the left part. This part. You've generated generative model, created import pre-label. Sorry, this side I'm saying. And use it to label data. So now the part one has ended. Now the part two, the second part. You've labeled it, and now you can access the label data to right, to train your discriminative model. So you can fit and predict, and this is exactly where the labels are getting used, because now you're trying to come up with accuracy. Okay, so you'll get some accuracy numbers at the end. Did you miss the accuracy part? So you can basically predict the accuracy, final test accuracy score 0.79. You can also compute F1 and whatever. So this is cage. This is what I showed at the top. But now let me give an idea of the same SMS. You can do something called joint learning. Okay? The difference I'll point out. So pretty much large part of this are same. The same labeling functions, etc., etc. So the data. But now you'll employ joint learning. Okay, so the joint learning algorithm comes here. Out of completeness, for completeness, we have also written how the label data can be obtained. Uh, so here you do the joint learning, and you do this between. So now you see something new has come up, something called feature model. So far we only had the labeling function model theta, but now suddenly a feature model has come up. What is a feature model? The feature model is for the model you're trying to learn, right? The end model, which Cage did not, or the data programming general paradigm doesn't care for. Okay, so this is the key, and maybe I'll just take a screenshot of this. This is important. This is what distinguishes. So you could have neural network, you could have logistic regression, any of these. Oh. So give us a snapshot. Okay, this is the differentiator. The joint learning component that differentiates the joint learning, right, exercise from the conventional data programming, which is what I showed earlier. This part. Okay, so you got an idea. So here you can basically use any model, right? So this model, the joint model that you have, the discriminative model, this could be a this could be a neural network, this could be an LR, which is being trained in conjunction with the labeling function. Okay, so these are some state-of-the-art algorithms, and some of these, which I said, we do joint learning. So this does joint learning. This is joint learning. I'll talk about the difference later on. So some of these do joint learning. These are um, basically cascaded. Okay, what is now the joint learning? It's a semi-supervised data programming through joint learning. Let's try and understand that part. So here I'm trying to give you the 50,000 high feet description without getting into details, right? The key features here are you have a feature model, which I showed you in that figure, right? This feature model, this part. This is a feature model dealing with. Okay, and could be a neural network model or whatever, right? And then you have your typical labeling function model, which I have talked about, right? That would be your Cage, just whatever. And then KL divergence you can measure between the feature model and the labeling function model. You can in fact measure different things between the feature model and labeling function model, and that those different measures are listed here. Okay, for example, the first one, what you are doing here, you're looking at how the feature model agrees with the label data. This is the conventional, who is going to give annotation, right? This is the conventional supervised class. There's nothing, no rocket science here. The second component is what? It's saying, well, on the unlabeled data, how much is the entropy of the feature model, right? This has been done in lots of unsupervised learning literature. So you don't want the feature model to have too much entropy. You want them to have some certainty on your unlabeled data as well. Okay. The third component is saying, well, now the third component is started bringing together the feature model in red and the labeling function model in white, in blue. So this third component says, if I were to look at the output of the labeling function model, GL I mentioned above is a label prediction from the graphical models. Okay, so this, imagine that you bring the G here, right? From a graphical model, what the label is, right? And then look at the feature models prediction on the unlabeled data. So agreement on the discrete output or discretized output of LF model with the feature model on the unlabeled data. Is making sense? On unlabeled data, how are they agreeing? Now you're looking at all kinds of consensus, not just consensus on labeling. Consensus with the feature function on label, unlabeled, on right now unlabeled. Now we'll also see labeled data coming up. The fifth component, sorry, the fourth component is looking at how the labeling functions perform on the labeled data. Now that's something data programming doesn't care for in general. So data programming is only creating the labeled data. But we are saying that no, you may want to use the labeled data to also calibrate your labeling functions. Given that you have labeled data, if you didn't have, it's another thing, right? So, right. So basically, measuring how good LFs or other or influencing, slightly influencing the LFs based on label data. Because that's only one component. I mean, all of these can be, you can plug and play. You can choose some of them, drop some of them as you want. The fifth component is how these theta perform on the unlabeled data. This is the conventional. This is what we have been using so far in the data programming literature. This is the conventional data programming objective. So in data programming in data programming, you don't have access to your label data at all, and there's no feature model. Right? So this is all they will do. Is this making sense? I'll just change the color to be, but I think any other color is going to create a conflict. And then the second last component is looking at the KL divergence, between the distributions of the feature model and the distribution of the labeling function model on combination of unlabeled and labeled data. So, probabilistic agreement. It's like a probabilistic agreement of LF and feature models on labeled and unlabeled data. That's the second last component. And the last component is what I spent some time on earlier. This last component is the quality guide for data programming, which I said has been very effective. The QJs, right? which can tell you how good one labeling function is with respect to one word. Okay, so this is assuming you have the label data already, right? Is this a big picture clear? Any questions here? Okay, so I bring an interesting perspective next. I say, well, all this is fine, but who gives you the label data? And that's exactly where subset selection can come. I think this needs a lot more exploration. Vineet has been exploring it further, right? I think this needs serious attention. How do you get that label data in the first place? I'll give one motivation to identify that label data. If you just choose it blindly, it might be redundant. You can choose it randomly. Random, by the way, is a very good, very difficult baseline to do. Right? We need to have experienced it. In many areas, random is not that easy a baseline to do. So it's a formidable baseline. But that doesn't mean you don't try to beat it, because when you look at large data sets, even random may not be good. Right? So, so you want to intelligently select the label data. I'm just giving you kind of one more example. So imagine that you have this photo album. Now you were confused about whether two images are the same or not. Imagine going to the user and asking, "Oh, are these the two or same or not?" Right? Why? Because the labeling function, the exemplars have failed. They're confused. So this would be such a nice feature. And Google Albums has provisions, but can we actually improve on the models? Right? Same, different, not sure. So this is the key, proactive data subset selection. The selected subset should complement and not subsume the labeling functions. I would say complement and maybe to some extent supplement, but not subsume. You don't want it to subsume, right? You don't want it to be redundant with respect to the labeling functions. So this, I think, needs a lot of investigation. I mean, you can, for example, go back and do privacy preserving. You can say, this labeling function is my privacy cell. Okay. That means I want examples, label data that is argmax over the conditional gain of argmax over x. The data to be labeled. When I say label data, I mean data to be labeled. Call it to be argmax over x of fx given the labeling functions. Something like this. Or some proxy for the labeling functions. So this is one way of doing it, right? But you may say that, no, I don't want them to be totally disjoint. I mean, they should have some agreement. Because if you look at this objective here, we are also looking at agreement. Why are we looking at agreement if you want the labeling function and label data to be totally complementary? So some agreement is also required. You also need some agreement between LF signals, labeling function signals, and feature signals through the label data. Right. So therefore, this kind of motivates also to look at the mutual information, IF. Would I look at IF x comma the labeling functions? Right. So therefore, I can say that IF, you may probably in practice, you may need a combination. Okay, I'm just leaving this as food for thought. In practice, you might actually need the mutual information of x comma some LF based on some. I mean, these are all proxies, right? So you can think of this as proxy of LF, and then another proxy of LF conditioning in the condition. I don't. I'm just leaving these as food for thought. But I'm going to give one last motivating example. Imagine you have these labeling functions LF1, LF2. right? And you have these examples: S1, S2, S3, S4. Labeling functions 1 and 2 are for two different classes. Labeling function 1 is for spam, right? Let's read it. If HTTP or HTTPS and comment text have return +1, otherwise abstain. It's for spam. Whereas LF2 is for non-spam. It's also called ham. Right? If length of comment is less than 5 words, then return -1. Else, otherwise abstain. Right? So let's carefully observe what's happening here on these two examples. For S1, which has true label +1, LF1, what does it say? It says 1. Labeling function 1 says it is a spam. Labeling function 2 abstains, which you are okay with. So there's no conflict. They are happy with it. It's like in some sense, maybe reinforcing also that could be a spam. On the other hand, in the second case, S2, labeling function 1, it abstains. And labeling function 2, it says, oh, it's -1. I mean, it is not a spam. Again, there is agreement, right? So overall, there's an agreement between these. But let's look at S3. Example S3 and S4 in the green, right? So here you can see that, now there's a conflict here. Labeling function 1 says, oh, 0, I abstain. Labeling function 2 also abstains. Now, this is a problem, right? Now, how, what should you do? Label. Both of them are abstaining. Whereas in S4, it's the other way around, right? You're basically saying, oh, labeling function 1 for S4 says, oh, it's a spam. And this says it's not a spam. There's a conflict. So these could be the examples that you should identify to be labeled by the human. That's what I've put in green. Can we do subset selection, choose label data using conditional rules? Is this motivation clear? Okay. So this can help you generalize for test data. Now by the way, I've shown features also. If you look at the features on the other hand, features F1, F2, I mean, these are very indicative of the right classes S3 and S4. Okay. Feature 1 seems to be triggering for spam, and feature 2 seems to be triggering for non-spam. And that seems to be very much in alignment. So feature space would benefit, right, through the label data. Okay, sorry, I have to very small. But however, what I want to still point out is, even if you don't do all that intelligent subset selection, even if you do some random subset selection or unsupervised subset selection, supervised subset selection, these are not MICG functions, not MICG, but simple submodular subset selection, right? Or you do random. I mean, these two better than random, obviously. And what we find most importantly is that if you use these for subset selection, you do better than a whole bunch of hand-picked schemes for subset selection. These are hand-picked, right? And you rather use some kind of intelligent subset selection than just handpicking. In fact, handpicking can sometimes do worse even than random subset selection. I'm not getting details of what is unsupervised and supervised. You can read the paper, but to give you a flavor of why subset selection matters. Is that okay? So you're encouraged to pick up research threads from here. I know we are kind of running out of time, so maybe I'm going to summarize the remaining very briefly. CODS is core sets and data subset selection. Now we have motivated this is a warm start setting. These were cold start, so this is warm start. There you have lots of data, labeled data already, right? Imagine that you have you already have access lots of labeled data. Even in such a setting, there could be a case for subset selection, for efficient training, for robust training. So these are the trained robust models, reduce end-to-end training time from days to hours and hours to minutes. There are a whole bunch of approaches, core set, and so on. I'm going to just give you some flavor of how you could tackle this problem. So CODS, oh, by the way, before I go to CODS, I just want to show you the one more thing, right? So this, yeah, I just want to show you this Colab notebook. I forgot to show this. The same Colab notebook I had given you earlier. You remember this SMS spam? I'd given you this where you put that logistic loss, right? You remember all the RVO conditions. I ran you through all of that. So in the same notebook, at the bottom, you'll also find how subset selection can complement. Okay, so just take you below. There's all gradient, conjugate gradient descent, a couple of others. Proximal gradient descent is also there. Why did I run it? So I shouldn't have run it. So all proximal and all of these are also put in here. Okay? Proximal gradient descent. I probably forgot to show you this earlier. So you can run through all of this. What I've also shown here is how you could imagine that for the same SPS span data set, if I use labeling functions, how I could use a semi-supervised learning, semi-supervised data programming learning. It's the same, the pre-process, the continuous scorers, labeling functions. So all that has been integrated into the same notebook. Okay, and you can basically check, right? The joint learning algorithm can compare its performance. So I obviously compiled it. Yeah, you can go over this. You can see how the joint learning performs with respect to the. Oh, yeah, I think I clicked on that wrongly, but yeah, I'll reload it. Okay, so go over this notebook. I'll point this at this. Okay. This old notebook probably is like a one-stop shop for all of you. So we'll go over this. Probably go back to CORDS. Sorry for the distraction. So CORDS is this, the goal is also very much motivated by conventional discussion on support vector machines. Right? So you know that support vector machines, not all the points contribute to determining a classifier. So can we determine that subset of points for efficient learning, for robust learning, for maybe efficient hyperparameter optimization, for efficient network architecture search, something that some of our colleagues are doing. Can that be done? So yes, that's exactly what CORDS investigates, and there are a lot of packages here. So here's a use case of CORDS: efficient, robust, supervised learning, semi-supervised learning, hyperparameter tuning, network architecture search. The idea is you don't need the entire data. Subset should be good enough. So here are a whole bunch of algorithms implemented. Several by our own students here. So I would say these. Craig is outside, but Glister, GradMatch, Retrieve is actually from our group, Cellcom, and these are some of the older papers. So I'll give you a flavor of one such setting. Probably, in fact, I have very detailed slides on convergence proofs. In case you are fascinated with our earlier convergence analysis, I'll kind of show them as glance to them. So let's start with Glister. The idea in Glister is that you have a training log likelihood, which is evaluated on the entire training data set U, right? But can we identify a subset of U which is relevant based on a validation set V? Can we identify a subset of the entire training set U by pivoting on a validation set V? Can the V tell you what subset of U would give the same effect as U? Right? And how do we do that? So here's the idea. So instead of having theta star argmax on U, what if you did a theta star argmax on a subset? So can we say that this is the same? Can we say that this theta star is as effective as theta double star, which is argmax over theta of LLT, theta comma, some subset, and S subset of U. And here I'm saying this is where the validation lens comes in. Can the validation lens help you? Okay, so validation lens. And that validation log likelihood, that validation lens is the validation log likelihood. I'll combine them in the next slide. But this is what I'm trying to see, the validation lens, to give you the S subset of the entire set. Is this motivation clear? We want the subset S of U such that the resulting model performs best. Now, you have to again keep this in mind that the subset selection algorithm needs to be fast. You can't make the subset selection a bottleneck. That will slow down the whole thing. And of course, you like to bask in the theoretical guarantees of subset selection algorithm itself. So this is the problem setting. How do we select the right data for efficient and robust learning? Select a subset that maximizes the validation log likelihood of a model trained on the data subset. Okay, so this what I showed in the highlighting in the blue here. I'm going to just use the same color coding. I'm saying that the lens that we wanted on the validation set is this argmax outside lens. I want a S subset of U of the training set with a particular cardinality such that the likelihood on the validation is maximized when you use the parameter theta from the inner loop in the inner optimization problem learned on the subset S. Theta is earned on subset S, but that theta leads to maximization of validation likelihood. I mean, this also is exciting and interesting because you're not limiting the use of validation to some, a for loop on hyperparameters, right? Sometimes you also wonder why validation is being used so ineffectively, right? Why can't validation itself be more tightly squeezed into the optimization? And this could be one way, one view of it. So, of course, instead of validation, you could also use the full training set. The validation gives you a generalization view. Right? Is this picture clear? Then the details are maybe more, we'll glance over them, but this big picture is important. This is the big picture of bi-level optimization. You'll find lots of bi-level optimization. In fact, you recall your midsem, you had a bi-level optimization, right? That bi-level optimization, you remember was it discrete? Did you have any discrete optimization there, or were both the inner and outer optimization continuous? Anyone? So both of them were when both continuous. There was lambda in both cases, right? There was lambda and there was a set of parameters theta. Both were continuous, right? They were both continuous. You can go back and verify. Okay, so here we have, of course, inner optimization as continuous and the outer is discrete. Okay, this is discrete. And the inner one is continuous. Okay, so now I'm going to go this a little fast. So what happens is if the inner optimization this is going to be really optional. Right? I'm not going to go into deeper details. But if the inner argmax, if it turns out to be either naive base, naive base classifier, or if it turns out to be nearest neighbor, under certain assumptions, it can be solved in closed form, and it yields an overall outer optimization problem, which is submodular. Okay? So outer optimization in the inner is naive base. The outer optimization for data subset selection becomes a feature-based function. If you have talked about feature-based functions, basically coverage function, right? Submodular function. Or if you have a nearest neighbor classifier as the inner optimization, or the inner optimization, the outer one becomes a facility location, which is monotone submodular, right? Okay. So this has been dealt with as early as SML 2015. The inner optimization problem, otherwise, is going to be difficult in general. Right? You don't have naive base and nearest neighbor being used nowadays. So if you have a more complex optimization problem which you have to solve, and then you're going to do subset selection, it's just going to be unmanageable, right? So, and it can also defeat the purpose of selecting a subset for faster training. What's the point of training? So one thing you can do is one step meta approximation. What you do in the inner optimization, you say, okay, I won't use the exact objective. I'll do this approximation. I'll set this to be theta, the previous iterates theta plus a gradient step on the subset. So I don't do a full optimization, right? So that's exactly what we have substituted here inside. So these are my approximations. So now instead of saying having an inner optimization, I just did a gradient one step update. That making sense? This is the approximation. So inner minimization is gone. But what is the advantage? Does this help? Okay, so it turns out that the validation log likelihood is now negative logistic loss, which is more realistic, right? Negative squared loss, hinge loss. You can have hinge loss, right? Negative perceptron loss. In all these cases, it becomes a cardinality constraint, submodular maximization problem. So now this is giving you something. Okay. I'll give you some slides where you can look at these additional proofs. And it turns out that if you have a negative cross entropy loss, then you have something called weak submodular optimization. So this I'm going to just quickly explain what is weak submodular. I didn't want to just present weak submodularity without a motivation. This is one motivation. What is weak submodular? But otherwise, it's submodular. What is weak submodular? In fact, there are two notions. There's a notion of weak submodular and there's a notion of pseudo submodular. Okay, so this is weak submodular on the right hand side. And a subset of it, I'll explain how it's a subset. I mean, it's a subset. The subset is called pseudo submodular. That's the left hand side. So the difference is that in the a function is pseudo submodular if the incremental gain of adding bunch of elements E from A. Right? So A, you have a set A, and A is disjoint from B. So let's say there's a B here, and then there is an A already provided. So for every, and B consists of lots of elements E. E is a canonical element from B. For sum over all the elements E given A is greater than or equal to some gamma times the function B function on entire set B given A. You all know what is conditional gain, right? It's all conditional gain. Weak submodularity says no. Weak submodularity, I won't look at just inequality on gamma. I'll relax it. So this is a relaxation. The moment I say relaxation, what would you expect? What would be a subset of what? So you're saying it's a min of gamma f b given A, which was already here, right? We already had that function on the right hand side. So this function comes up again. Gamma f b given A, right? That's here. Comma 1 by gamma f b given. The min of these two. Because we have not put any constraint on whether gamma should be less than 1 or greater than 1. Okay. So do you think weak submodularity will be general or more specific than pseudo? I'll just take 5 more minutes. What do you think will be more general? What? Huh? Weak will be more, yeah. Because this min of these two, right? Exactly. In fact, this is the, you have gamma weakly, and weakly is in fact more general than submodular. It's more general than pseudo submodular. The place where pseudo submodular and weak and submodular they intersect is called is basically modular functions. So F is submodular if and only if gamma is greater than 1. Okay, so that connection with gamma comes out here. So F is submodular if and only if gamma is greater than 1. Okay, all this is optional slides, but just to give you the bigger picture. For non-submodular functions, gamma is between 0 and 1. If F is monotone, then pseudo basically becomes weakly. That's also an interesting connection. And especially when you have non-monotone functions, the weakly submodular definition, that makes more sense. The more general gamma, weakly. That's this one. Okay. This is the big. And then what happens if you have the greedy algorithm applied here? So the greedy algorithm you can apply to monotone functions. The greedy algorithm achieves a 1 minus e raised to minus gamma approximation for gamma weakly or even pseudo submodular functions. And for non-monotone, it's basically gamma e raised to minus 1 by gamma, much weaker. Okay, so I just want to conclude this one interesting use case. So now we have already found that by simplifying the inner optimization, right? We have done well. But even that is not good enough because we want to do the inference LLV on this. You have to do this for every element E in S, right? You have to so you have to do this conditional gain of LLV of E given S can be expensive. Oh, there's a problem. Can you hear me? This can be expensive. So there's one more step approximation that you can do, which is I'll do a Taylor series approximation. Okay, so LLV theta is now of theta plus some argument is LLV theta, which is kind of more stationary, right? The theta is the previous epoch theta, plus a dot product measuring the alignment of the gradient on the subset with the gradient on the validation set. This is very interesting. Measuring, alignment of gradient, element of gradient. That's a good validation and training set gradients. The subset and the validation set gradients. This is done in each epoch of the iteration of the greedy algorithm. But this is interesting because now, because of this very important approximation, you don't have to do multiple forward passes. The LL theta can be used as it is from the previous epoch. You just have to take a new element, look at the dot product, new dot product, right? For each element that you add, you just measure the updated dot product. So that is probably the most interesting thing, and the reason I brought this up is there are lots of functions which try and operate on gradients. Okay? Looking at gradient alignment. In fact, there's a follow-up work of ours called grad match. There's been a previous piece of work called Greg, which actually looks at gradients. So gradients themselves are very interesting. This is the overall idea. Right? You do subset selection, you find new set of parameters. You do DSS data subset selection, and then you find new set of parameters. You alternate between these two. Okay, but without getting into too many details, I just want to conclude with this important point that even in terms of theory, you get order 1 or epsilon square approx of convergence. You remember now the previous analysis we have done. So you can show that the algorithm converges to optimizer in order 1 by epsilon square. And another interesting point that comes in the result is this: in those many epochs, the min over the validation loss and the optimal loss, right, is upper bounded by something that involves again this dot product. The same dot product I showed in the previous one. Okay. Dot product of the gradient and the subset. I have very detailed slides on these. How I can post them as optional reading, and I kind of highlighted in yellow these slides. The glisted algorithm is there, and assume the validation subset training law satisfy the equation that this dot product is greater than equal to 0. Dot product comes up in multiple places, so I'm just highlighted that. The convergence proof is all provided here. I'll share this with you. And this led us to the next model, right? Where you say, okay, you can measure dot product, you can also measure the difference between the two gradients. Right? The dot product is highest when they are aligned. The difference is also 0. You're trying to minimize the difference of the gradients when they're aligned. So this is another paradigm. You're measuring the difference between the gradients. That gives us the grad match algorithm. But interestingly, this gives you 3x speed up with no loss in accuracy. It just maybe, and if you want some loss in accuracy, you're okay, like 1-2%, then you can get 10x speed up. And we have shown its results even for hyperparameter tuning. And you can also show results for robustness. 7x to 5x to 7x speed up when you're trying to do robust learning. Because validation data set gives you robustness, but also gives you speed up because of the subset selection scheme. I'm not going to go into any further details. So please do look at pods and Decile. Decile is the deep, diversified interactive learning. And again, this features a whole bunch of algorithms. A lot of them, the whole idea, and again, interactive learning is you don't select one point at a time, but you select a subset of points. I think there's a lot to be done at the intersection of data programming, interactive learning, right? That's the reason I'm quite excited about presenting these. So think of future research problems in the project if you want to let that unfold in this direction, or any kind of follow-up research you want to work on for papers. You're more than welcome. I think this interactive learning is interesting because you're not again looking at selecting individual points at a time. And the Decile also it introduces many data augmentation techniques so that the generalization performance is good. And there are several state-of-the-art algorithms that have been implemented. So data augmentation would basically mean, I flip images, right? So somebody may ask, is the active learning doing the same thing that data augmentation would do? You don't want data augmentation to be unnecessarily done by active learning. Active learning should add the additional value. That's why we added data augmentation. And we in fact found that a lot of the so-called benefits previous active learning methods celebrate, they get undone when you do data augmentation. So that's the reason, at one point I want to highlight. And we've shown how Glister, for example, you can do pseudo, you can identify hypothesized labels or pseudo labels on the subset to do better active learning. Okay, I'll not get into these now. The thing is, we've been very benefited by use of these techniques in multiple applications, including OCR and so on. A lot of video analytics work. We actually were benefited from the use of interactive subset selection. So, yeah, I think I had too many slides. But these applications, this kind of helps conclude the applications front, right? Yeah, I'd like to end with this picture. I think so. You're welcome to contribute or use different aspects of someone. We'll stop here. You can. I mean, I'll share with you a spreadsheet where I have maintained. Where is it? So where we have maintained. Yeah, here. So CORDS. Also, there are very nice notebooks. Collab notebooks. Likewise for semi-supervision and hyperparameter tuning. I'll share all of these with you. You can try out them. This is for data compute efficient learning. So interesting to see is hyperparameter tuning work, especially how you get 10x speed up. So I'll share these with you, and then the Decile part are again very nice notebooks which you could make use of. So I'll share these notebooks with you. Welcome to try them out. They're of course there on the Decile page. Any last question or anything or comment? Anyone on the call? None, then thanks for your attention.